This talk is sponsored by the Central Virginia node of Commonwealth Cyber Initiative, and we are a state program establishing Virginia as a global center of excellence in cybersecurity research. And we support research, workforce development, and innovation through cybersecurity, autonomous systems, and intelligence. And every year, CCI and CVN sponsor research and experiential learning projects, and today's speaker is a recipient of that funding. And I'll drop those links to the CCI website and the CVN website in a bit. And so today we have Dr. Eyuphan Bulut, and he is an academic within the Virginia Commonwealth University Department of Computer Science. And over the past decade, his academic interests have revolved around wireless networks, mobile computing, and cyber physical systems and social networks. And his work has explored diverse areas from mobile crowd sensing to direct vehicle-to-vehicle charge sharing systems. And he's also secured research grants like one from the National Science Foundation focusing on improving IoT networks. And in recognition for his work, Dr. Bulut was honored with the Best Demo Award at PERCOM in 2020. His dedication to VCU's computer science department has demonstrated by consecutive teaching and publications award from 2017 2019, highlighting his commitment to both excellence in education and research. And today he's going to speak with us about wireless smart home intrusion detectors and more. Enjoy, and remember to stay on for the Q&A segment after the talk.
Thank you for the introduction. So I would like to start with also thanking the CCI-CVN for funding our research, which is on developing an intrusion detector using the wireless signals in houses. And so let me start with that motivation actually. So the we are actually motivated by the by the current home security system. So the way the current home security systems the work are actually like there are some cameras deployed throughout the house, or maybe some motion sensors, contact sensors on doors and windows, and they're trying to kind of monitor if there's a break in happening, or like some sort of unexpected moment is happening, right? So, and this considering that based on some statistics, every 13 seconds, some type of burglary happening, these having such sort of a system is actually an important thing, right? But on the other hand, the story is different actually. Like when you look at the statistics again, like only maybe less than 30% of the US households have a security system deployed, right? This has many reasons actually. One of the main reasons is because of their high cost. Then there will be a new, sensors, new devices that needs to be installed inside the house, right? If you look at the average cost is around like $700, which could be, even like upper in more than even $1,000. So there are also other reasons, of course, like people don't believe that completely that these systems, prevent the crime totally, or there are some false alarms, things like that. They don't want to have those things. But the fact that not all the houses have that home security systems, and mainly because of the costs. But on the other hand, we have a different situation with the Wi-Fi network. So meaning that over 92% of the houses in US already have a Wi-Fi network. And then this is not just one single device. There are other devices that are connected, including the laptops, phones, IoT devices, which are throughout the, spread throughout the different floors of the house. And on average, there are actually like 11 devices in a regular house that connects to the access point, and then does some, Wi-Fi packet exchanges. And there are also like some sort of like newer technologies which kind of aims to deploy multiple of these access points at different, floors, what we call Wi-Fi mesh systems. So it is actually increasing the, the ubiquity, like the availability of these wireless signals throughout the house. So we have a already, ubiquitously available system, which is Wi-Fi networks. On the other hand, we have only 30% of the houses having the home security systems. So motivated by these facts, actually, our motivation, like what we are trying to achieve with this project is actually, can we leverage these existing Wi-Fi infrastructure in houses, and then the signals, right, that is propagating inside the house, reflecting off from the furnitures, whatever environment, even from people, anything in the houses that are reflecting from those and then arriving to the, the other end. Can we leverage these ambient Wi-Fi signals or even the low-cost Wi-Fi devices to build a low-cost intruder detection or some sort of a home security system that can monitor, some potential break-ins, things like that? So that was the main motivation. And then once you're trying to, find out like if there's a break-in is happening, we need to know where the break-ins are actually happening, right? The statistics tells us that most of the time the burglars are using the front doors, back doors, or the windows, sometimes the garages. So the thing that, can we identify if the doors are open to like windows are opened with using the Wi-Fi signals? That's the question. And another type maybe of these intruders can be considered a little bit differently. Recently, increasing trend is like people are coming to your front porches, and then they're just grabbing your packages that are left by Amazon or other delivery carriers, right? And then this is a significant issue actually. Like right now, based on some statistic recently, 17% of the Americans have had a stolen package in 2022. And that's happening. So can we also leverage those Wi-Fi signals that are uh, penetrating even through the walls and going outside the house, maybe just front porch, to monitor an activity, an unexpected activity, and even be able to differentiate it from the regular activities, right? That's the question. So let me give you a background a little bit on what kind of technique we are using. So we said we are going to use Wi-Fi signal for sensing purposes, right? So Wi-Fi is initially designed for communication, the exchanges, but recently trending idea is, can we use Wi-Fi signals for sensing? And it requires some type of like information, low-level information. But in general, the idea, like the benefits of this is, first of all, you can track the activities without having any variable on the body of the human, right? Or without any other type of sensor. And then these signals can go through the wall, and then you can even identify things happening behind the wall, right? That means like, it is beneficial, or it has an advantage over the camera systems which are blocked by the wall, which will not be able to see the behind the wall. That's why you need another deployment behind the wall. But most of the metrics that we get from these Wi-Fi signals include like RSSI, what we call, which is received signal strength indicator, and which is more like a high level information about these signals. But recently, thanks to some devices that are developed, people can also reach out to more finer information, which is what we call channel state information. So this is like a physical layer wireless data, which can give you like a view of the signal at different subcarriers within the Wi-Fi band. And now using that information, you can catch some fingerprints. So, and that's the goal. If we can we use these metrics, like these measurements, especially the CSI ones, to be able to understand some intruder actions? So a little bit more background, like what is this channel state information? So Wi-Fi systems use actually like what we call orthogonal frequency division multiplexing systems. They are using different subcarriers, and each subcarrier has some CSI information that can be broken into like amplitude, kind of like related to the signal strength, as well as the phase information of that signal. So, but these signal, it's not that very straightforward, because like these signals will be not just going from a transmitter to a receiver directly. They will be also going in a multipath manner, meaning they will be reflected from the objects in the environment. That can be static objects, they can be moving objects. So it's a combination of some static paths as well as some dynamic paths. But we need to kind of identify and then see that part, and then be able to see what has changed compared to the dynamic side of it. So just to give you like what the CSI really can do, like, I have two pictures over here. One of them is showing two different actions, like a person standing between a transmitter and then a receiver of a Wi-Fi, device. And then it is basically standing, not doing much, and then now sitting on a chair. As you see that over these different subcarriers of the Wi-Fi channel over a time, when we get these measurements of the CSI, these are amplitude measurements, you can see that the standing activities happening at different times have similarity compared to a sitting activity, which is totally different. So this is kind of giving us like a fingerprint of your activity. So you can do you can analyze these CSI metrics and even differentiate different movements happening in the environment. And the other thing, I have an example over here is, let's say we have a TX and RX, again, transmitter and receiver, and then the person is just passing in between them line of sight. This is showing that we can clearly identify the moment that the person is passing the line of sight. So it is like working like, like the laser beam sensor, but with the wireless signals. Okay, so having this background, so what's the Wi-Fi sensing system in general, and then what are the steps? So the way it works is like we need to collect some CSI data from on the receiver side as the transmitter send the signals, and then this CSI information is nothing regarding to the content of the packet. Again, it is obtained from the header of the packet. So you can send an empty packet, and then but we can still reach out that CSI information. It is unencrypted. It is reachable. It just gives an information feedback to the transmitter side, so it can adjust the data rates or the which subcarrier is used for the data communication. But we are just leveraging that information for sensing purposes. Okay, so we need to collect the CSI data from on the receiver side. Then we need to do some processing of that data because the raw signal by itself will not be helpful. That requires different steps like denoising, feature extraction, and dimensionality reduction. Then if your data is not enough, you can even or not distribute it through the time. Well, you can do interpolation, or if it is changing in different days, we can do things like detrending of the signal. But once the data is ready, like in the way that you can you extracted the features, then we can either use a machine learning model which can understand those, like differences that you have seen over here, the similarities between different actions, and or some statistical metrics. From there, once a model is trained, you're going to use that model for predictions. That was the basic step. So from our project's perspective, what are our challenges, right? First of all, we need to extract the Wi-Fi CSI data, as I said, right? But the way it in the last decade or so, people have been using some available tool that has been developed, but they are not scalable. I will mention about them. So we need to find a system that is scalable, low cost, and that can even be run as a separate standalone device on the edge. And once we collect that CSI, now we need to find out like way to process them in a way that we can recognize those specific intruder actions, which can be far from the devices, right? That could be activities like door or window openings or package thefts from the front door, things like that. Any kind of movement that can look like an intruder. And the other thing is, all right, you can develop a solution for a specific house, but how are you going to make it work it, or a specific room, let's say, how are you going to make it work for a general, meaning from different rooms of the house or for different houses? And can you make it also work in a way that it is independent from the environment, or the different intruders will be resulting the same? And even more, I will mention that in the later as well, but can we also separate the actions from the moments of the owners, things like that? So the final challenge actually in this specific research is, which was actually a research project more on the commercialization and prototype development. So we also worked on actually a real prototype development towards that. It's still an ongoing part, but I will try to mention the steps of that and where we are with that as well. Okay, so let me start with what people have been using and why, what are the problems and what we did to address that. So the first, like there are a couple of tools, as I said, in the last decade that people developed, and most of the Wi-Fi sensing solutions available in the literature or like people doing research are basically using this Intel 5300 network interface card. And there are also newer tools like Ethos CSI, as well as some more like generalized hardware like USRPs that has been used for this specifically catching those Wi-Fi signals. But overall, these devices need to be connected to a computer like a laptop or things like that. They cannot run by standalone, and they cannot be deployed like a large scale throughout the house to get that CSI information from the existing devices, or even add to that and increase the number of devices. And then they are not energy efficient, and they will be most of the time running these machine learning solutions in the cloud by sending the collected data to the cloud. But again, most of the studies never did this type of online development. They mostly collect the data and then they just run it offline manner. So to address these, like to get a more scalable solution, actually, thanks to some good students I had, like we develop a tool, like or maybe what we call a lightweight solution, let's say, that runs on small tiny devices like microcontroller units like of this size. It's very small. I will talk about the details of this device as well. But this is a tool that lets you be able to collect the channel state information from the Wi-Fi signals in the environment, and then that runs on a small tiny device. And it's also an open source project that we let people you be able to use it in GitHub. And there are so many users of it already so far, and then people are using it there for their own Wi-Fi sensing projects. And but compared to other tools, let's say I have like this table over here, which basically shows that our size of the microcontroller, and then since it's a standalone solution, right, it is compared to the other ones which are very big, and then in terms of the cost, we are basically just talking about $5-10, while the others require a host device like a laptop to be able to run it. And then the other things are, it is very lightweight, it can run by itself as a standalone device. So you can just take this and then put it to different parts of the house to create redundant Wi-Fi, packets on top of the existing Wi-Fi packets to increase the coverage of the house. So these are important for deploying this like a large scale Wi-Fi sensing system in a house. On top of these, actually, we additional features of this tool is include, let's say, you can send a packet from each of these microcontrollers can run as like a transmitter or a receiver or even a passive listener, meaning they can even listen the other devices' signals in a passive manner. They don't need to be the ones that are like used added outside as an additional to the existing Wi-Fi devices. And they can just grab like sniff the existing signals in the house that's happening between the IoT device and or your laptop, and then also with the access point in the house. And we do have other tools like this app, let's say, which is an Android's app, which shows that clearly that this transmitter is sending data to this receiver, and then which is basically just showing the extracted CSI information. So that's just to show what we are receiving. It's of course not making sense, but you can develop an app which tells you that what happened in between them. Let's say if you do some activity between these two of them. So that's just additional tool on top of what we have with this CSI extraction. Okay, so we have the tool which can be deployed, which can extract the CSI easily. And how are we going to use that CSI data, right? First of all, as I said, we need to do some filtering, and these are a couple of steps that we did, but we did more, of course, beyond these. But so we are basically doing some filtering of the data, so to get rid of the some anomalies, or using a sliding window of the CSI data, maybe like a 1 second over 1 second of data, which is referring to kind of like 100 packets, 100 CSI data, 100 CSI frames over all these subcarriers, which are changing based on the Wi-Fi version that you have. But these ESP32 support up to like 64 subcarriers, and on some of them are null, and when we exclude those, only 52 of them are having a meaningful data. Once we collect those data, we can also do some we do also do some dimensionality reduction using principal component analysis. So instead of having all these different subcarriers metric, we have single one, which is a combination of the most important ones from the data. And then from that collected data, we train a deep learning model, deep neural network model, and then we create the model to be able to use for the predictions that will come from the future CSI data. We did look at the other things like just using the statistical metrics as well, and I will mention those in other slides. So let me start with a quick video and then showing what we really see in the signal. This is again from the principal component analysis. We just show one single column of data as a student performs some opening of these doors. So yep, in the static environment, we don't see much changes in the signal, but when the student opens the door, as you see, there are some response in the signal that you can understand. And there is a transmitter and a receiver in this environment, which just basically can see those changes. But when the student opens the other door, you are gonna see that their signal changes will be slightly different than what you have seen with the first door. And but when you, even though it's not going to be exactly every time you get in or open across the same door, there will be some similarities which will not be uh, clearly seen, maybe like when you look at this graph. But thanks to the the neural network, we will be able to understand those changes. So this is a little bit longer video, but the goal is, or I am trying to show with this video is different doors, different windows, or different movements happening inside the house will have different fingerprints in the signal, and then we can learn those fingerprints, and the next time when there's an opening happening in that same environment, we can understand which one is actually opened. And regarding that, I actually would like to show some results to you with that. So in this, let's say, small first experiment or first result, I would like to show this is collected in a like an environment where there were like the four doors, and it was like a front door, bedroom door, bathroom door, and a whole closet door. It's an apartment context, I guess. And it was, so student go ahead and open each of these doors one by one, and collected some data. And we had just one transmitter and a receiver in the environment. So then we use some portion of it for testing, some portion for training, just to see if this is reasonable, or we can identify which door really is opened. So here are some results. So it's basically showing that we can whatever that happened in the testing data, like based on our training, we can actually understand which door is opened. Like we can predict that over 90%, 94%, which door is opened very clearly, successfully with these steps that I told you in the previous slides. But again, this 94% accuracy is within that 1 second time duration, and we have all these overlapping CSI windows, which is just with this stride of one or two moving window, right? And then we are collecting those. We are just getting the CSI data for 1 second, and then we are just feeding it to the neural network just to get the prediction. Out of these 1 second windows, some of them are overlapping, we can get 94% high, like the successful prediction. But that doesn't mean that, the overall accuracy will be 94%. Essentially, if you look at the like a maybe 5 second duration, it will be saying that over that 5 second duration, 94% of these 1 second overlapping time windows will be predicted correctly. But if you look at an entire 5 second, and you can just say that what happened in that period, you can say that with a majority voting of these 100-second overlapping windows, you can basically say that 100% accuracy, I can predict which door is opened. So this is just more like depending on your reaction time. If you want to get an answer within 1 second, that's what you get. But with a longer second, you will be able to increase that accuracy. So we look another thing, let's say, okay, the previous one was the opening of doors, but I talk about the case that where these signals can penetrate through walls, right? In that case, can we understand, let's say, if somebody is walking behind the wall, right? Or if they are walking also, if it's not just their presence, it is their walking direction as well. So to do that, in this case, we had the hallway, and then we put some like one transmitter over here and other two receivers on the each side. And then the idea with this is we even like, when you send a, transmitter sends a signal, it will be talking to these RX directly, but to as well as some of the signal will penetrate through the wall, and it will hit the other wall or maybe other objects moving here, right? And it will come back to the receiver side, because that's the, the connected the receiver or the other one as well. So the uh we want to kind of create like the avoid the dominance of the signals that's happening in the line of sight. So we created actually some kind of like a beamforming effect by putting a aluminum container around these transmitters and let the signals penetrate through the wall actually. So of course you can develop a more professional system, but the idea was let the most of the signals go through the wall and then reflect from the moving objects and then come back to this one. So with this, as you can see in these results, like as the person is, let's say, moving from the right to left, which we see that based on some metric that we developed, which is looking at the, the standard deviation of the road, like standard deviation among the subcarriers. So we can see that the red part, which is like this receiver, actually RX2, is like this part can recognize that movement first, and the other one is recognizing. That means that when the person is moving this way, you can identify that there the movement over here first and the movement over here next. So it's basically, it can tell you that the person was moving from right to left. On the other way, when the person is moving from left to right, you can also see that as the blue one is picking the first. So by deploying just 3 of these devices, one or two of them are RX, and with one transmitter device, we can even understand what's happening beyond the wall, as well as the walking direction of the person. So that was another result which can help understand like things behind the walls even more than just their presence. Another result that I would like to show, let's say, is can you identify, like the packages, let's say, that are taken by the strangers from your front porch? We did actually test it, collect data and test the system in 2 different environments, and we use different types of packages, like, and also to be able to actually differentiate, this package theft activity. We did actually consider different types of activities, let's say these 5 of them, and student that was going, like this area and was knocking the door or maybe just standing there or walking by, but there were 2 activities, as you see, which were very similar, meaning package taken and a package placed. So if the a package carrier brings your package and plays it and then goes, it should be able to be we should be able to differentiate it from the package taken, right? That's why we wanted to look at how different it is. Can we really understand that? In one of them, you're coming with the package and dropping it off and then just leaving, right? In the other one, you're coming without the package and then you're just getting that. So we can see that there is difference. Then by camera, of course, you can see that, but can the signals understand that level of, difference? And in the apartment setting, we did use 1 pair, but in the house setting, we did put, the RX was inside over here. This was the RX also behind the door as well, but we put some of these also outside, just for the sake of things that if we can, what is the accuracy first? But of course, you can keep these RX and TXs inside as well, by also forcing the signals mainly going out, right? And okay, results. So results are a little bit less compared to the other ones, but the main reason is like we are around like 75, like the 80% accuracy. But again, these are within the 1 second. Like if you increase this duration, these will be, if you just wait to collect 5 seconds of data, which is reasonable, and then before doing a prediction, these will be jumping to close to 100%. But overall, these confusion matrices tells us that, you know, the most confusing parts are the package taken and the package placed activity. So that, which is reasonable, right? They are very similar activities, just the time moment that you deal with the package and what you do with that package. Are you just leaving it there or taking taking it out, right? So but the way we can increase this is like putting more of these devices, collecting more data, and then but this was just a testing of the idea, which sounds like it can work, and then depending on the time that you will be doing your prediction, this can be even further increased. And I would like to also add another result, which is just like we just did, like, yeah, related but not totally measured in the way that they introduce actions. But the idea with this result was actually we let's say asked, this is actually a part of like a capstone project that our undergraduates are doing. So the idea was we collected data when one, three, or five people walking randomly inside a room, right? And then can we identify really how many people in the house are like moving in that specific room. uh, the result, as you can see over here, is again promising. You can achieve you can predict how many people are actually moving in the house. But of course, like we ask the students to move randomly, depending on their actions, these things can change. But this was just giving you an idea that what we can achieve in terms of understanding the multiple intruders. As you also see that we didn't look at, we collected data with 1, 3, and 5 odd number of people, because the one that we collected with 1, 2, 3 was not as high accuracy like this one. And then the main confusion was coming from the between the 2 and 3 one. It is the same scenario over here. So you see that differentiating between 3 and 5 people is still challenge compared to 1 to 3 people. Okay, those are some results, and that shows out that there are promising things can be done by just using the Wi-Fi signals, right? But how we can generalize, right? Well, we collected data for each experiment separately, and then, but you cannot do it like maybe to the level that we do during the experiments. And we would like to actually avoid training data collection at every house, and we would like to develop a generalized solution, make it environment independent solution or subject independent solution. Towards that, actually, our idea was to use a federated learning approach, which mainly used for privacy preserving based learning solutions, but it also lets us be able to learn from different environments and then share that knowledge between different clients, different classifiers, so they can train like do some changes in their model and learn more environment independent solutions model. So our solution, what we call Wi-Fi federated, was actually tested in this specific scenario. We collected actual data in 10 different locations of a house. They were more or less like they were like specific to the activities listed here, like sit, stand up, sit down, and standing activity. But you can also, of course, like make these specific to the, the more intruder actions. But the idea is over here, we just use some of these rooms for data collection, and we develop a model by letting these each like the model over here and model over here and model over here be able to train some time, and then share their learned information of weights, that what we call, and then let them average at the central server, and then continue get that averaged weight at each of them again, and then continue that learning by using their individual data again. So no learner model is sharing their data, but they're just sharing their weights, what they learned, and then they're just then averaging. The central server is just averaging those weights and sending them the average weight models in rounds, and which can be helping each of them be able to focus on the features which are not specific to the environment but specific to the actions performed. So with that, actually, we have some results over here. So what we did is, like, again, we trained using the data from some subset of the locations, right? But we tested on total unknown rooms. And then with, let's say, that unknown room being a living room over here, we see that the model trained on other rooms, which without using any data from that new room, can predict that what activity was performed, let's say, with 80% accuracy without any data. But if you get a few data, labeled data from the new environment, you can see that that also increase the performance or the accuracy of that system. So, but this is compared to a system which can only train, which if you don't have any data, of course, you will be predicting that a random action like around 25%. And if you have some data from that new room, if you are training a model specifically by using the data from that new room, you will have that accuracy increasing with the more data as well. So this is basically saying that with the federated approach, we can learn, develop a model for what kind of activities we would like to develop, to predict those activities without using any new data from the new environment, and that will work in these new environments. And the last thing I would like to also show that is like, okay, like these were all studies which were like we collected the data and then in an offline manner, we kind of saved them for testing, and then we did process everything offline. But our goal within this project is actually towards a prototype development, right? So that there is not actually a pro solution like that. There are some commercial like some companies that have started to have some products that are trying to detect these actions that are happening inside the houses, but it's very new area, hot area, and we would like to do some addition to that actually. So, but this requires some work, like we need to get the live CSI data and then put it to a time series database, which needs to maybe because of the low memory of the devices, maybe in the SP32 specifically, we need to kind of sample some of the CSI, not use all of them, not save all of them, right? Then from that trained model, which is a generalized solution, we can then apply or give it to the model and predict our result and display that result if that is needed, or maybe send it to, like the owner's device, let's say. That's something ongoing work, like 80% of the work is done so far, and we are about to finalize that actually. So this is something related, but I don't have a prototype right now to show you. So overall, with this work, what we aimed is like we aim to develop an intruder detection system using the Wi-Fi signals, which are already available in most of the houses, which is going to be a low-cost solution. And then, of course, privacy preserving compared to the cameras. And then it's scalable thanks to our device that we develop. I showed you some results regarding the door openings, which doors are opened, detection of the humans, walking direction through wall, as well as package thefts. And we also had the idea like how to develop a more generalized solution using the federated learning approach. And the final goal is also like to make this as a prototype, which can work in a live manner and predict those changes in real time and send it to the owner. So, but there are some future directions as part of this research, as also I would like to discuss over here slightly, which is I talk about the case where we deploy those tiny devices, right? Which is over the counter available, and then we can reach out the CSI information. You cannot do that with other devices so far, but the number of devices probably will increase as we go. But as I said, like we are creating our own redundant Wi-Fi packets in these environments. But ideally, the goal is there's already Wi-Fi signals happening in the houses, right? The devices are not sending a data every time. There's a low rate compared to what we use. So the goal is actually, can we get still a good sensing accuracy using only the what's happening in the in the house between the devices? So the low rate, depending on activity, you can still identify, with low rate Wi-Fi packets, some type of sensing. But can you also augment this low rate to be able to increase the sensing accuracy? Something we are currently looking at it. The other thing is like the adversarial side, meaning that if we can identify or extract the CSI information and even listen, sniff the signals, Wi-Fi signals happening in the houses, like an adversary can do the same, right? These signals go outside. So they can even understand, if you look at in the other side, somebody approaching to your house and listening the Wi-Fi signal happening in your house, and then some kind of doing it over a few days, can understand maybe you are at home or not by, passively listening and analyzing those signals. So that's scary, right? So, but that's true if they need to a little bit get close to your house. And that's something we are looking, and we are developing solutions actually to prevent that. And the other thing is more generalization of the what I have presented, it meaning, what if there's a pet in the house and then it is moving? Can you still identify that that's a pet, not an intruder? Or I was also assuming that these systems also we're gonna be, we are considering a time frame that house owner is not expected to be at the house, and you're within that time frame, you're not expecting any movement in the house, right? Then if there's a movement happens, then we can identify it. But if we to make it more generalized solution, what you can do is, the owner doesn't need to turn the system on, or if I can identify, or we can identify with this system and differentiate when the owner does the same action compared to the intruders. Can we identify that was the owner and not the intruder? It's very hard question though, because like, the differences on the signals happening due to the door openings will be very similar to when the intruder does it, but it depends on the intruder's way of, breaking in the house as well. But that's something that we would like to look as well. So as an acknowledgement, this is my group that is working on these Wi-Fi sensing, and thanks to my PhD students, these are happening. And we did have some RU students working in the summer, and capstone project students contributed to this project. And the funding is coming from the CCI Central Virginia node.
Okay, thank you so much for giving this talk. We really appreciate it. Thank you everyone for attending. Um, Next week we have Dr. Lee coming in. So I'm gonna drop the link for that in the chat if you guys would like to register. Thank you everyone for coming out, and we really appreciate it.